discussion on induction machine and start our discussion on power electronic. So last 2 weeks we talked about induction machine. We start from the construction and we try to find the good models. We discussed different models, T models, gamma models, simplified gamma models, and further simplified gamma models. And then we settled with one of them. It's a simplified gamma model, as you can see, and try to use this model and try to derive the equation for the torque and its relation to the speed of machine. We find the torque as a function of the machine speed. We find that there is a Tmax, maximum torque, and we find the speed that torque max happens at that. So we find that the Tmax shown here is not a function of the rotor resistance, but it's function of lambda s, which was the magnetizing flux of the machine and has inverse relation to the leakage inductance. We also find out that S max, the sleep that maximum torque happens at it's only function of the rotor resistance, and it has an inverse relation to the supply frequency and leakage inductance. We find the torque speed characteristic. It's something like this that we have shown in the below figure. We talked about that close to the synchronous speed, somewhere close here, it shows almost linear behavior. But then when we start to deviate from the linear speed, we also start to deviate from the linear behavior, and you can see it there. We find that S max for both motor and generator mode are the same, and we find out that the standstill torque or start of the torque of machine when machine is stopped, not rotating, TSS, is much smaller than Tmax. And we said that it can be a problem, because if our motor is starting with load, under the load, if the TSS, your driving torque of the motor, is less than your load torque, you never start rotating. Your motor will be still, because you need a driving torque larger than your load torque opposing that. Or even if it is larger but is slightly larger, your acceleration will be slow, so it takes a long time to get to the maximum torque you want. So we said, okay, one of the first issue we need to solve is that how we can increase this TSS, or this standstill torque or startup torque. And for that, we said, okay, let's use the rotor resistance. Said the maximum torque is not a function, Tmax, shown here, is not a function of RR or rotor resistance, as we know. But S max, it means the S speed related to the S speed that this maximum torque happens, is linearly related to RR. So said, okay, let's use this to solve the problem. So if we have a wound type rotor, in which RR can be increased. So the solution we are going to discuss cannot be applied to cage motors, because in cage motors you don't have any access to the rotor circuits. You cannot go and increase the rotor resistance in any way. And we said, okay, let's increase it. So we add some resistance to the slip ring to increase the resistance. But for the sake of simplicity and have a better control and handle over the machine, let's assume that ES over omega S, which is equal to lambda s, it is the magnetizing flux. Let's assume it is constant. In fact, as we said, to have the best performance, in most of the cases, we want to keep gamma s high at the rating, but we cannot force it and push it to be more because it gets the motor or machine saturated. So you will see this more, that we try to keep gamma s constant, or at best we decrease it. We rarely may push, if never push it to increase it, because it may saturate the magnetic material that we have used inside the machine. In that case, if we start to increase the RR, Tmax or maximum torque remain constant, shown with this violet color, so purple color, the maximum torque remains constant. But by increasing RR, the sleep of that torque max happen at that is increasing. So what's happening? S max 2 will be larger than S max 1. So T max comes to new point. And when we increase R more, we find a higher S max, call it S max 3, and T max come here. By pushing the curves there, you can see that still the synchronous speed remain constant because omega is constant. We haven't changed the supply frequency of the motor. We are only changing the rotor resistance. We keep the same synchronous speed, but we push the maximum point lower and lower. And by that, as you can see, here are our standstill torques. It is increasing. In fact, we can increase the S max to point of S max 4 until the T max, the maximum torque, happen at the standstill, shown here. So by changing the rotor resistance, we can achieve the T max at the standstill. The maximum torque we can generate with motor, we generate it at the standstill. But we shouldn't push our luck. If you add the resistance more, the S max increase even more. And by that, now you came to this new point. But we are interested in the standstill torque. And the standstill torque in this case is here. Once more, the standstill torque has decreased. So we increase the RR, but it's not we can increase it as much as we want. After some point, we start to decrease the standstill torque. Any question here? Okay. Let me summarize some of these points for your future points if you want to come back and review what's happened here. So, first of all, we find out by increasing RR, we can will result in increasing S max. Then we said if we increase it enough and design it properly, we can come to the point that S max means the sleep at which the maximum torque happens be equal to 1. In this case, TSS standstill torque or startup torque will be equal to T max. In the previous slide we showed it with S max 4 and here with this orange color. We also said R should not be overly increased as this results in the reduction of the startup torque. We are talking about this figure and you can see here the S max is even larger than 1 and then we get a standstill torque or startup torque which is smaller than T max we used previously. So this one is shown with the dashed curve, and in previous slide we show it with S max 5. We have used similar approach in shunt DC motors to somehow control the startup torques. What was the problem there? Why we didn't like this solution very much? What is the problem of adding a resistance to the circuit? What is the most important disadvantage of this method? Any idea?
Reduce the efficiency?
Exactly. The problem is that resistance means loss, and we start to losing some power in that resistance. So we cannot use it for long term. In fact, this method is usually just used for the startup. As soon as the speed gets large enough, we get rid of the resistance. We short circuit the slip rings and bypass the resistance that we have added because they are decreasing the efficiency of the machine. And let me write up that too, that the solution should be used for short-lived startup. Oh no. The startup intervals otherwise the power loss in the external resistance, call it with Rx, should be prohibitive. The slip rings springs are usually shortened together once the machine speeds up to a sufficiently large value. Okay. Summarize our discussion here. And here was increasing RR or R external. Any question up to here? No question? Everyone done writing? Okay. So let's do one example. So the machine of example 2 with RS equal to 0, calculate, here is calculate the standstill torque. So for this we are going to use equation 10. Equation 10, we introduced it, we derived it last session, that TSS will be equal to 2 max over 1 over S max plus S max over 1. We know at the standstill S is equal to 1. We also have calculated the S max in the previous time, so we have everything. We also calculated the T max, so it will be 466.7 over 1 over 0.273 plus 0.273. T max will be equal to 237.1 Newton meter, which is only about 50% of T max. So without adding, pardon? Oh, sorry, yes, thank you. Thank you so much. So, and here is the answer. Without adding any additional resistance to the rotor, the TSS, as we predicted in general case, we know from the different machines that we have worked, is much smaller than T max, and this is very much the case with many induction machines, and it was a problem, and it is a problem, and usually they try to solve it. Previously, in previous years, they tried to use method like this, adding the rotor resistance, but we get soon to the other solutions that is more modern and more common nowadays. Any question here? Everyone done writing? Okay. Okay. Said the external, ask us to calculate the external resistance needed to make the standstill torque equal to the maximum torque, assuming that the machine was wound rotor. Actually, in example 2, the machine was cage motors, and I cannot emphasize enough that you cannot add any resistance to the cage motors. But if these are wound rotors, we can do it. It's simply in a very simple scheme. If it is your wound rotor motor, then you have 3 slip rings. These slip rings are connected to some brushes, and from there we add the external circuit that we are interested in it. And you remember it's a 3-phase. Also, not only a stator is 3-phase, rotor is also 3-phase. But everything is balanced, so very much the same resistance in every phase. Now we are asked to calculate that R external to find that T standstill torque or startup torque be equal to T max. We know that S max is equal to RR over XL. So S prime max over S max will be equal to R prime R over R R. We want to have the S max to be equal to 1, but originally it was 0.273. In that case, RR was 0.3, but now we have added some external resistance to each phase. The very simple calculation, at the end you will find out that R external will be equal to 0.80. And in this case, TSS will be equal to T max will be equal to 466.7 Newton meter. The problems with the startup of the induction machine is even more complicated than this. It's not only the low torque, we have also problem with the high inrush current in the motors. But for the sake of this course, I think as this is enough here, and we can move on from the startup torque and its issues and solution from now. So similar to discussion that we have for the DC machines, one of the goals of this course from the start was to control the machines. For the speed controlled, for a long time, in fact, in industry, they prefer to use DC machines for adjustable speeds. That's why for a long time, even the subway of Toronto was used DC motors, or streetcars of Toronto was also using the DC motors, or let's say DC machines. But we have problem there. So the problem there for the DC machine is that, first of all, they are expensive. Secondly, they are high maintenance because of all the brushes problem that we have talked about it. And thirdly, they cannot be used in some hazardous atmospheres. So we have problems there. But at the other hand, with the induction machines, for a long time, they considered as a very constant speed machines, because as we discussed, they usually work at some speed very close to synchronous speed. And even with load changes, it doesn't deviate very much or close very much to this synchronous speed. It remains in a very close range to that synchronous speed. So it was considered as a constant speed machines and constant speed motors. But this has changed from very start, because all of the problems with the DC motor, they try to find solutions. We are going to, in this few next slides, we are going to talk about just the main idea of them, not get very much detailed and technical, but later we may going to discuss them more in the next module of the course, next chapter, that we talk about the power electronics. But not all of the solution was related to power electronic. One of the simplest solution was changing the number of poles. So we said the synchronous speed is a function of the number of poles. It was 2 over p omega s. So if we can, let's say, double the number of the poles, we can decrease the synchronous speed to almost to the half, exactly to the half, and the speed of the machine almost to the half. So it was a very simple solution, and in fact it has been used for a long time. In fact, for many of the applications that we have in domestic use, this is still in use. If you see some induction machine in some of your home appliances that just have 0, 1, and 2, just 2 speed and 0, it's maybe it's in cage motors with 2 different kind of number of poles that it changed between them. So it's basically using changing the synchronous speed which was 2 over p omega s, or the intercept of t omega characteristic with omega axis. So basically we just change the p, we change the synchronous speed. It's the induction machine, it remained very close to that synchronous speed. The speed of machine has changed. What the problem is that it can only be used in the cage motors, because in the wound rotor you need to also change the number of the poles in that rotor, and it gets very expensive, sometimes very hard to do it. So this solution is only good for the cage motors. But even with this limit that it has, it's used in most domestic applications, and a good percent of industrial ones. The other problem with this solution is that it has discrete steps. In fact, in many cases it has just 2 steps. It's changed between 1 to 2 ratio. And the other problem with this solution is that it is more expensive winding for motor is needed. So we need a more sophisticated stator winding. It means more cost. Any question here? The cage motors, discrete steps. So it doesn't mean that you can smoothly change in any speed you want. Usually you have two steps. For example, 4-pole or 8-pole. You can choose between two of them. You cannot say, okay, I want to go from 0.5 poles. You cannot do that. Even it's not that 4-pole, 6-pole, 8-pole, and 10-pole. Usually just two steps in many practical cases, 4 and 8. You can change between them. So you don't have a smooth control over the speed. You can just have two different speeds if you want. Any question here? Can I go to the next slide? Seems so. The other solution is already known to us. It's increasing the rotor resistance. So as I said previously, we have these slip rings here. And then we increase the external resistance. So if we have a low torque speed characteristic like this, as I said previously, the synchronous speed remains constant, but we can achieve different operation point. Here is increasing R external. The problem is that this solution is restricted to the wound rotor. We cannot use it for the cage motors. The other problem is that it also is on discrete steps. So you have, for example, 4 different resistance and you add it step by step. It doesn't mean you can take any resistance in a very smooth way to go and move between them. So again, discrete steps. And finally, as we previously mentioned, we have mentioned that the problem is high losses. We are adding resistance to the circuit. It means more losses. But it doesn't mean we are hopeless with the induction machine. In fact, we have some very effective solution. And one is changing the source frequency, or omega s. But by changing omega s, we should remember that we have some concern about the flux in the machine. We want to prevent any saturation, and flux was related to ES over omega s. We want to keep ES over omega s constant to prevent any kind of saturation. So supply voltage Vs must also be changed to keep ES over omega s constant. Otherwise, saturation may occur. So we change the frequency to be omega 1 omega s1 2 over p omega s2 2 over p omega s3, or here 2 over p omega s4. But because ES over omega s is constant, Tmax remains constant, as I said, because it is related to ES over omega s square, and here is lambda s, which is constant. So the Tmax remain constant, but the synchronous speed start to change. It's like that we are shifting everything. The flux is constant, but we are changing the frequency. So here, if we have a load torque speed characteristic like this, we can achieve different speed if we want. And here we are decreasing both omega s and ES. The solution is very similar to one of the solutions we have for the DC motors. It was when we keep the flux constant and instead change the terminal voltage. We use it for the separately excited one or shunt one, mainly for separately excited one, if you remember. So this solution resembles very much to DC motors with constant flux and decreasing Vt. Here we also keep the flux constant and decrease both ES and omega s. One of the most important advantage of this method is it is continuous. You can virtually achieve any speed or torque on the load torque characteristic that you want. The other advantage of this method is that it is very efficient. In fact, they use this method when we are interested in high performance applications. That's why it takes longer for them to come to the home. It was started more in industrial scales, larger one. But nowadays, some of the refrigerators also use similar techniques to increase the efficiency. Everything seems good. What do you think is the problem with this method? Why it takes some time to be very popular in industry and everywhere? Any guess? Pardon? Yes, it was expensive for a long time, but the good thing is that price of power electronic is always dropping. So this problem is not as severe as it was before, and it gets easier and easier every year, but it requires a three-phase variable voltage variable frequency power supply. You need a power supply that both its frequency and its voltage is changing, and for that you need power electronic. In fact, in many cases they call this in a shortened name that as variable frequency drives. And we are going to talk about this more in the next chapter of this course. Any question here? Are we good? Can I go to the next slide? Or you're still writing? I think I can go to the next slide. The other solution is supply voltage change. So in this case, we keep the frequency constant, so synchronous speed is not going to change. It remains constant. We also don't change the rotor resistance, so maximum slip or S max remains constant. But by decreasing the voltage, we are decreasing the torque. In fact, we are decreasing the flux. That's why we are not very much worried about saturation here. By decreasing VS, the voltage, if we are in large industrial motors, RS is zero, almost zero, so we're decreasing exactly ES. Omega is constant, so flux is decreasing. There is no danger of saturation. We are not worried about saturation here, but we also decrease the torque. So what's happening? The maximum torque is decreasing. So here we keep the omega as constant, but we decreasing Vs. As a result, ES over omega S always remain smaller than omega S max, so there is no danger of saturation. If we have the torque speed characteristic like this, load torque speed characteristic, then we can achieve some speed control. But as you can see, is not a large range of speed change. So this solution doesn't very effective for a very huge speed changes. It usually work in a very small range of the speed. So the speed does not change or does not have to change. So it's good in cases that the speed does not have to change widely, just for those cases. But what is good about this method? Any guess? We only change the voltage, we don't change the frequency. So it is very cheap in fact. It can be done much easier. In some cases, they don't even use some power electronic. Even some auto transformer, a special kind of transformer, is used to achieve this control. So the good thing here is it's inexpensive. But it doesn't, as I said, because of all the problems we have here and some that I haven't mentioned here, it's not used for any kind of load. In fact, in most of the cases, it's only used for the centrifugal loads. Before I go into the last topic of this section of the course, I just need to emphasize that here was a more conceptual approach to these problems, and this, in fact, the methods of the speed control was considered like more an introduction. For example, the changing the frequency is not limited to one. There we have several methods there that we can use. But here I just try to discuss very much the concept to you and not get too technical. But enough of that. Let's go to the final discussion of this part of the work, and it's about the more accurate model. When we try to use the gamma model, simplified gamma model that was RS and we use XL, we use this model in fact, RS, XM, XL, RS. So here we have VS, we have RS, and here we have ES. This model was very useful for us and we used to derive all the equation because in many large induction machines, RS is so small that we can ignore it. In that case, ES is almost equal to VS. So everything gets very easy. That's why in all the equations that we have derived up to now, we was talking about ES over omega S. There was no VS. If you go and revisit equation 9, 10, and 11, there was no discussion of VS. We use ES all the time. And then it's very practical for large induction machine. But when we get to the small induction machine, less than 10 kilowatt, it's not a very good assumption. RS cannot be ignored. And in those cases, we cannot say ES is equal to VS. The equation we have derived can still be used, but each time you need to calculate the ES from the VS and then go and find and use it in the equation. So here what we are trying to do is say, okay, let's modify the equation that we have derived for more general case when RS cannot be ignored. In that case, T torque will be equal to 2T max S over S max plus S max over S. It seems up to now appears to be very similar to the previous equation that we have, but it's going to change. Plus 2 over root of 1 plus XL over RS square, and here 1 plus 1 over 1 plus XL over RS square. Much more complicated. For sure you don't need to memorize any of this, but you need to know when you are going to use this equation or when you prefer to go to equation 8, 9, 10 and 11 that we have previously discussed. But even situation is more complicated than this. T max, which is the maximum torque if the machine operates in motor mode. In other words, when S is greater than 0, the max will be equal to 3p over 4, but this time no sign of ES, but we use VS. VS square over omega S 1 over RS plus root of RS square plus XL square, which is equal to, also can be written as 3p over 4 Vs square over omega S 1 over RS 1 plus root of 1 plus XL over RS square. As I mentioned, you don't need to memorize any of this. You just need to know when you are going to use it. So when RS over XL is small enough, or XL over RS is large enough, greater than 5, you can go back to the previous model that we have. You can ignore the RS. But if it's not the case, which is usually for the machines with rating smaller than 10 kilowatts, you need to go and use this model because RS cannot be ignored. Any question up to here? Any question? Okay, go to the next slide. The situation even gets harder because also S max is different. So the maximum torque occurs at slip S max, but S max is slightly different. S max is equal to RR. Here's the same, but here is the difference. RS square plus XL square. The root of RS square plus XL square. Or if you like, you can write it as RR over RS over 1 plus XL over RS square. This root at the denominator is going to be repeated very much in these equations. So now RS is added. If you take the limit of all this and try to approach RS to 0, you go back to the equation we have previously. But the problem is that these equations are going to be used when RS cannot be ignored, cannot be considered as 0. The other thing is that now the generator mode and motor mode previously have the same maximum torque. Now the maximum torque are not the same in these two modes. The S max remain the same for both, but the torque, maximum torque, will differ. So in generator mode, the maximum torque also occurs at S max formulated above. But remember that, notice S is less than 0 for generator mode. However, its value is larger as T max gen over T max. We know that T max in the generator mode is negative. That's why here I have used absolute value. Will be equal to 1 plus XL over RS square plus 1 over 1 plus XL over RS square minus 1. Any question? So without that assumption, everything gets more complicated, as you can easily see here. Can I go to the next slide? So if we try to draw the equation here, there are the characteristic here, the torque speed curve. What is happening? The S max for both are the same, but now the T maxes are different for them. So let me put in some absolute value here. It will be something more like this. And it doesn't matter you are working with omega or n. So the only difference here will be or ns s, and here will be s max ns or s max ns. The important thing is that we lose the symmetry we previously have in the figures. As you can see, is not symmetrical anymore. So not symmetrical anymore, because T max gen is greater than T max. Here we are in motoring mode, motoring region, and here we are in generating region. Okay, any question? Everyone done writing? Okay. Can I go to the next slide? Okay. So the final example of this part, and we are done with the induction machines. Says a 4-pole 25 horsepower 60 Hz 460 volt induction machine has the following parameters. Calculate the maximum motoring torque and sleep at which it occurs. So first of all, let's calculate XL, which is equal to XLS plus XLR, will be equal to 1.106 plus 0.464. We find 1.7. And XL over RS is not 5 or greater, so you cannot ignore RS. We need to go to the more sophisticated formulas that we just found. So T max is equal to 3p over 4 Vs square omega s over 1 Rs plus root of Rs square plus XL square will be equal to 3.4. Here this is line to line voltage, but we need to line to neutral voltage here. So multiply by 460 over root of 3. I will be really disappointed if you make the same mistake, such a mistake in your exam. I emphasized it several times that in this equation you need the line to neutral or phase voltage, not line to line, while usually rating of the induction machine is given to you as a line to line voltage. Square over 377 multiplied by 1 over 0.641 plus 0.641 square plus 1.7 square. So T max will be equal to 140 Newton meter. S max will be equal to RR over RS square plus XL square will be equal to 0.333 over 0.641 square plus 1.7 square. S max will be equal to 0.96. Not that hard. When the equation are given to you, it seems very easy. Any question?
Why did you divide the
As I said, the voltage given you there is line-to-line voltage, but we derive all this equation based on the pair phase model. And in pair phase model, you need line to neutral voltage. Any other question? Are you done writing here? Can I go to the next slide? Okay, I believe so. B asks us to calculate the startup torque and the torque at shaft speed of 1600 RPM. So because this term 1 plus XL over RS square is repeating very much, let's once calculate it and get rid of that. So it will be 1 plus 1.57 over 0.641 square. It will be equal to 2.645. So T will be equal to 2T max 1 plus 1 over 1 plus XL over RS square S over S max plus S max over S plus 2 divided by 1 plus XL over RS square. So T will be equal to 661.5 over S.196 plus 196 over S plus 0.756. So we just put the numbers and find the equation. We calculated the S max and T max in the previous part of the question, in the previous slide, and we just calculated this term that we can simply be replaced here. Now that we have the equation for T, calculating the torque at different slip is very easy. So TSS is in fact T at S equal to 1. So just put S equal to 1 here and you will find that TSS will be 109 Newton meter. One of the part that question has asked. So have N equal to 1600. First we need to calculate, and we know N S is equal to 120 FSP. So S is equal to 1800 minus 1600 over 1800 will be equal to 0.111. Just replace this S in the equation we just find for the T, and T will be equal to 214 Newton meter. Any question here? That's okay. Everyone is done writing, no? Okay. Everyone is done writing? I assume so. Okay. Last part, I'll calculate the maximum generating torque and slip at which generating torque and slip this time. Generating a slip is not going to change. It's the same. The maximum generating a slip is the maximum motoring a slip. The only thing we need to calculate is the maximum torque. So we know S max will be also 0.192, is not going to change, but T max gen over T max will be equal to 1 plus XL over RS minus 1 plus, XL over RS square plus 1. Oh no, sorry. Plus 1 at denominator minus 1 at the denominator. It will be equal to 2.645 plus 1 over 2645 minus 1 be equal to 2016. It's more than 2 times larger. So T max gen will be equal to 2.16 max multiplied by 240 calculated in part A. T max gen, its absolute value will be equal to 531.8 Newton meter. 96. If I want to go and draw the speed torque characteristic, here we have torque. Okay. Here we have omega, or n, sorry. Here if we have 1800, the synchronous speed, the T max happen at 1447, and here at 253. Here we have 240 T max of motor mode. And here we have minus 531.8. And we said that startup torque is 109, So it will be something like this. Torque speed characteristic. The question has not asked. I just want to give you a better feeling of what's happening here. Any question?
What was the criteria where we can no longer ignore RS?
So as long as XL over RS is greater than 5, it's a good idea to ignore RS. If not, it's not a very good idea. And it usually happens when the rating of the motor is greater than 10 kilowatts. Usually you can ignore it. The criteria holds. But for smaller induction machine, usually it doesn't hold. Any other question? So with that, we reach the end of this part of the course. So in general, we started very much the construction and the concept of the induction machine, how it works, why we call it induction machine. We try to find model. We find T model, gamma model, simplified gamma model, further simplified gamma model. We used one of this model, actually one of the simplified gamma model, to derive the only equation and we find the speed torque characteristic. And based on that, we also discussed the control speed techniques that have been very conventional and have been used for a long time for the induction machines. With this part of the course will finish. I